We've been talking about randomized decision rules, and recall that a randomized decision rule is a probability distribution on the action space, which is determined once data is observed. And then we also talked about how to make a non randomized decision rule randomized, quote unquote, and express it as a randomized decision rule which puts all of the mass at the one point. And then also we talked about that if there's a no data problem, if we don't have any sample data, then we can analogously have a randomized action, which is again a probability distribution on the action space. So let's look at an example of the no data problem. Now this is the matching game in our textbook. It's on page 12. And so the way this works is you and your opponent each have a coin, and each person decides whether the coin will be displaying heads or tails, and each person puts their coin on the table. But they're both covered up, so neither one knows what the other person chose. Okay, so let's say you choose is the action, and we'll say that little a1 means you chose heads, little a2 for tails. And then your opponent, of course, that's the unknown part of this. So your opponent, if they choose heads, that'll be theta 1, and then if they choose tails, that'll be theta 2. So since this is since we have a finite number of actions and a finite number of possibilities for the parameter, we can just look at a loss matrix. So let's think about this. If you choose heads and the opponent chooses heads, then that means they match and you win $1. So that means your loss is negative. Remember, in terms, we look at things as the textbook says, sort of pessimistically, statisticians do. So in terms of loss, smaller is better and bigger is worse. So in the case where you win $1, that's a loss of -1, and so forth. So let's say you choose heads and the opponent chooses tails. Well, then in that case, they don't match, and you actually would lose $1. And you see that in the loss matrix. And so let's suppose, we keep playing this game. Well, it wouldn't really work for you to just always choose the same thing. So you have to come up with a strategy. And so from a probability point of view, you would maybe think, well, I'll just always choose heads with probability 1/4, and I'll always choose tails with probability 3/4. But then you may be wondering, well, how in the world would you do that? So we would have to be assuming a little bit of latitude when you play the game. But nowadays, of course, there are random number generators, and so one way you could do that thing I said is you could randomly generate a number between 0 and 1. And if that number that's generated is less than or equal to 1/4, then you could choose, I think I said heads, and then if it's, say, bigger than or equal to 1/4, right, so if it's between 1/4 and 1 inclusively, then you could choose tails. And so you could use a random number generator to do that. So we have to come up with some game plan, and that's, from a probability point of view, that's one way to do it. Like I said, choose heads with some probability, P we'll call it, and then tails with probability 1 minus P. And so that's what we have diagrammed here. And so that would be a randomized action. And in my notes here, I suppose that little p is 1/3. And these are old notes. I've taught this class before, but long story short, my videos were lost, so I'm having to redo these. But anyway, that's where I talked about the random number generator and how that can be done. Okay, so we'll come back to this example a little bit later. But a convenient way to express these randomized decision rules is what we see here. And recall that this notation where we use the angle brackets, this is how we take a regular decision rule and turn it into a randomized rule. This would be the randomized rule which always chooses A1, which chooses A1 with probability 1. And so let's see if we can convince ourselves that this expression that we see here really does represent the decision rule that we come up with. So remember that our action little a1 was we choose heads, and then a2 is we choose tails. And we're going to choose action a1 with probability p, and a2 with probability 1 minus p. And well, so I think that's going to work. So let's see. Well, if we take a look at going from this notation here, if we look at what that delta star would give evaluated at A1, remember that delta star is a probability distribution on the action space, and the probability of choosing action A1, that should give us a little p. Okay, so let's substitute for delta star this here, because that's what we called it up here. And then this is really the sum of two functions. So the first one evaluated at A1 plus the second one evaluated at A1. Well, this P times that angle bracket A1, I'll just call it that. P times angle bracket A1 evaluated at A1 is the constant P times 1. Because remember, this thing here, this angle bracket A1, always returns 1 if A1 is the input. Right, that's the rule, that's the probability distribution that chooses A1 with probability 1. That's why it outputs a 1. And then over here, this part, this is going to multiply 1 minus P times, and then now let's focus on this part. Well, angle bracket A2 chooses action A2 with probability 1, and chooses action A1 with probability 0. So since we're evaluating this at A1, we're going to get a 0 for that part. So what we have is, in fact, little p, and that is what we should get, because delta star is the probability distribution, which, if we have represented it correctly, it should be equal to A1 with probability p. Or it should be a probability mass function which, when evaluated at A1, gives little p. And then similarly, we should be able to see that if we evaluate this at little a2, it will give us 1 minus p. And so I would encourage you to go through the steps and do that for yourself.